Okay, so this is lecture 7, and there were some good questions last time, and a few that I thought about more. And so I do this sometimes. You know, I love when you guys ask questions that sometimes I can answer them pretty well at the time. Sometimes to have a good answer, I need to think about it and put something together. So what I did, you guys see the screen? Make sure. Okay, so I'm not going to go through all of this. I'll post this. I think I have already posted this on Canvas, so you can read in more detail. But we talked about the degrees of freedom methods and how they could be more conservative and more liberal, and how, you know, we talked about, like, if you increase the degrees of freedom, well, there were some that thought it would be more conservative, some that thought it would be more liberal. So really, to get a good sense, if we do an F-test, the F statistic has 2 degrees of freedom, right? There's numerator and denominator degrees of freedom. And what we're interested in looking at is what happens when you change the denominator degrees of freedom. So if we say we fix the numerator degrees of freedom at 20, and then we look at various F distributions as we increase the sample size. And you can think of a critical value in the tail and what's going to happen as you, like, let's say at 2.5 or 2 or something like that. What's going to happen as you increase the denominator degrees of freedom? How, do you have more or less area under the tail as you increase the degrees of freedom? Well, you can see that the distribution gets more pointed and you get less area in the tail as you increase the denominator degrees of freedom. So that means you'd be more likely to reject the null hypothesis. So it would be a more liberal approach to increasing the degrees of freedom. So we have various methods to estimate degrees of freedom, and we before I close this out, by the way, like I said, there were 3 or 4 questions that came up last time, and I put some responses. And in fact, this one, what's the benefit of using less than full rank modeling? I pretty much talked about it last time, but I put together a paragraph or 2, maybe even more, you know, clear possibly than what I said, but along the same lines of what I said. And then there was a good question about what in a test, if you don't want to compare to 0, you want to compare to something else. And you can see what I said about that. So this is posted on Canvas, and I'm going to close out of that. So we kind of are segueing back into the denominator degrees of freedom, and how when we talked about mixed models, how when you're doing inference for the fixed effects and tests and estimation involving the fixed effects, how what we do is we develop these test statistics, and then we can estimate the parameters that are in those test statistics when we use maximum likelihood estimation. But we have to figure out the best degrees of freedom to use that's appropriate for that test statistic. And there's various methods to do that. And I didn't spend a lot of time talking about those specific methods, but they're basically called containment, between, within, residual. That's like ignoring the correlation in the data and just treating it like it was independent data. So that's usually not going to be very good. Satterthwaite and Kenward-Roger, asymptotic. So those are the 6 methods that you can use. If you don't say anything in proc mixed or in the equivalent in R, they'll pick a default method for you. So the question is it the best one to use or not? And then we looked at the fitness data that we talked about previously, and then I just sort of go through these methods and show what the degrees of freedom would be for those methods. So I just want to mention a few things. I think you guys can, go through these slides yourself. I'm on a quiz. I'm not going to go into really detail, like asking you please figure out degrees of freedom and so forth. I just want you to get the basic idea of these. Just a few comments that I have. One is the residual and the asymptotic methods, which are going to be the most liberal because they're going to have the highest degrees of freedom. Asymptotic is infinite, right? Infinite degrees of freedom. So whatever that asymptotic distribution is, you're assuming that. And that's going to be very liberal and not a good approach. The residual method also it's going to ignore the correlation in the data. So I would not, for longitudinal data, I would not suggest using either one of those. In SAS, the default, if you have a random statement, is going to be the containment method. And that method is okay, but I did figure something out, and this is after teaching this course for over a decade. I looked at this in more detail earlier this spring, is that what it does is it's going to search for, I guess I'm going to talk about this a little bit more than I thought. So the containment method, let me just go back to that slide. Or if you say method equals contain, that's going to use the containment method to estimate degrees of freedom. And that's a default in SAS when you have a random statement. Okay, so this last bullet point tells you how that's calculated. So if a predictor is named somewhere in the random statement, DDF is set to the rank of the combined X and Z matrix associated with this named predictor. And one of the implications is that if you do the regular random statement, if you do it this way, if you say random intercept subject equals ID, there's no predictor in there, right? So in that case, the degrees of freedom associated with group time and group by time is going to be 32, okay? But we talked about last time about the fitness data. And and we had this table where we broke down the sums of squares. Let me get to it. If I can find it. So here's our table. And then actually with the fitness data, sorry, this is it. So we have the total degrees of freedom, and then we break it down into different sources. And then we talked about how the test for program, the best test doesn't use the residual mean squared error in the denominator. It actually uses subject within program. And how that made sense because that's a between subject source of variability. And we compared the expected mean squares to show that to get the best F-test, use that mean square. And its associated degrees of freedom is 8, okay? Where does that come from? Well, we have 10 subjects, and there's 5 subjects per group. So you think of in one group, there's 4 degrees of freedom. And then in the other, there's 4. So there's 8 degrees of freedom. So it's pretty intuitive that we have 8 degrees of freedom there. So it makes sense for test for program, the denominator degrees of freedom would be 8, okay? But you only get that if you use, if you do go with the default approach, you only get that if you specify it this way. If you say random intercept, subject equals ID within group, okay? So this, you guys may be familiar with this by now based on 6612, but this, what that means is you can think of that as ID within group. Okay, that's sort of the SAS notation for that. So really to get the accurate degrees of freedom, if you're going to go with the default method, is to use this approach. If you have multiple groups and there's a bunch of subjects in each group, you're going to get better estimate degrees of freedom specifically for that test for group if you use this approach as opposed to this approach. I saw somebody raise their hand. Elise, yeah.
Yeah, is that regardless of how you assign IDs? So like if I gave a unique ID to every participant regardless of group, should I still do it that way?
Yes, very good question. And yes, the answer is yes to that. That's even if you have unique IDs across the study. Yeah, good question. So that's something I learned, you know, just fairly recently. So you see the difference. If you have subject within group, the test for group has 8 degrees of freedom. If you don't, even if you have unique IDs, you're going to have 32 degrees of freedom. So it's going to be a more liberal test, more likely to reject the null. So the other thing I'll say about degrees of freedom is if you have a pretty good sample size, it doesn't matter as much. Once you get let's say 100, a couple hundred or something like that, if that's your sample size, then there's really not going to be that big of a difference, you know, because you know, as a sample size increases, the distributions will start to converge to, you know, to the asymptotic distribution, and you will see less differences. One approach you can use, I would say, like if you're unsure about, you know, I don't want to have to remember to put ID within group, or I'm not really confident about the containment method or between within, which R doesn't, they don't really have those. R has I think their default is actually like asymptotic, but you can specify the Satterthwaite and Kenward-Roger methods. And I think those are decent because they're more conservative. I think when you're in doubt, I think it's probably good to go with a slightly conservative approach. And so like here you can see that test for group 8 makes sense. They're slightly conservative, you know, it's a little bit less than 8. Why is it 7.98? I'm not exactly sure, but I do know that these methods tend to be a little bit more conservative. So that's why we have a slightly lower degrees of freedom for group. And then for time and group by time, you can also see that they're a little bit lower. The between within, real quickly, is kind of intuitive because it takes the total residual degrees of freedom, so that would be 40 for these data, and it says, okay, if we have 8 to do the between comparison, so the group is based on between data, between subject data, and we establish that there's 8 degrees of freedom there, then whatever's left over, the 32 would be for within subject comparison. So that's in a nutshell, that's what the between within does. So again, like I said before, I'm more interested that you understand out of these methods, like the 6 methods that we have here, which ones are more conservative, which ones are more liberal, which ones are clearly not going to be appropriate for longitudinal data. And I would say those are the asymptotic, unless you know the covariance parameters, which I've never come across a data set where I know the covariance parameters. So I would say that's usually not appropriate. Residual is not appropriate for longitudinal data because you're not taking into account correlation in the data and repeated measures. So it comes down to the other 4. And when in doubt, I would say it wouldn't hurt to use the Satterthwaite and the Kenward-Roger methods. And like I said, I think I said this, these are available in R in most of the methods, as well as SAS. So you can specify those. Are there any questions? I know that I didn't spend a lot of time on these slides, but you can read through these slides, read it for the general idea, that's fine. Any other questions you guys have?
Why for the start with and the KR method, the t-test, the DF is different from the f-test DF?
Say that again, Randy.
For the interaction term, group taps times time, and we get 11 for the t-test, the DF, but we get 32 for the f-test, the DF.
Okay, talking about this column here.
Yeah,
Why you're asking why are they different, or
yeah. And for t-test, it just goes to 11.
yeah. Um, I have to look at that more closely. That's a good question, and I'll have to review that and then get back to you on that question. It's a good one. But you know, again, the pattern that you see is that those degrees of freedom, they tend to be less, right? So they're going to yield more conservative test results specifically for Satterthwaite and Kenner-Roger. Off the top of my head, I just can't remember, you know, what's the difference between this column and this column. So let me look at that and get back to you on that question. Any other questions that I may or may not be able to answer that you guys have?
Professor, there is one question. In the approach of containment, the group size is changing. But my question is, can we customize the groups as in the K value so that we can group accordingly, or it is a random value it creates?
So you're talking about
Containment approach where the group is 8, 32, 8, 26.
So that when you say you want to control it, I guess I'm not quite clear on what you mean by that.
If you are considering a simple K means grouping, at that point we assign the K value. So if here we are doing this approach and we are getting some kind of groups, so I'm asking which approach can be a better way, the way you said residual is not good. So in similar way, do you think containment approach is good for grouping purpose, or which one will be a better approach?
I think it's fine for if you have like clustered data, or you have number of subjects within each group, and you establish that in the code that you've identified the groups and subjects within groups. I think containment's going to work fine, and in fact, it may yield the same results as other methods like the between within method, and in some cases Satterthwaite and Kenner-Roger method. It may be equivalent to that. So I think it is fine. It's a fine approach as long as you specify the model correctly and use the code that identifies what those groupings are. That would be my response to that. So yeah, so that's in a nutshell, you know, degrees of freedom. Again, the big picture is, you know, for linear mixed models, to do inference in linear mixed models, a lot of cases our models will simplify. Like if we just have a random intercept, we can think of the ANOVA approach in breaking down sums of squares and getting associated degrees of freedom. But for a lot of models that are unbalanced or where you may have missing data or just a more complex specification of the model, you can think of developing test statistics, you know, that are functions of parameters in our model, and then we estimate those using maximum likelihood. But we have to get, since the models are more complicated, we have to estimate degrees of freedom. And, you know, like when you run code either in SAS or R, a lot of times you just do it. You don't even think about this issue. But if you don't say anything, it's going to pick something for you. That's one of the points. And so I think it makes sense. And I'm talking to myself because for many years, I didn't really pay attention to this very much. But it does make sense to think about, you know, the degrees of freedom and what might be best to use. So going forward, as we analyze data sets and I present those, we can look at the specific issue as well.
I feel like when I read the literature, I never see people say what method they use.
Yeah,
So
I agree with you. I totally agree with you. It's something that's just not discussed very much.
But if you were to change it in like, you chose a different one, do you think it's important enough to like mention in methods that you used a different than the default?
Yeah. Yeah, again, I think it is good. I mean, I don't see a downside to it, honestly. Like if you're writing a research paper and you've analyzed longitudinal data, writing a sentence like, and if there's issues of space, you can always stick it into a supplement or something like that. You can put more detail there, but it shows that you know what you're doing. And honestly, like if you write a research paper, it shows that you really thought about it. And it's maybe even more important if you're writing grants, like to describe in details, because like when you're writing grants, what are you trying to do when you write a grant? You're just trying to show that you know what you're doing, really, right? So the more detail like that you can put in, you're going to convince the reviewers that, yeah, they know what they're doing, so I'm going to give them money so they can do the research, right? So I do think those kind of details are good. Obviously, you don't want to overwhelm with details, but like writing a sentence on that I think would be helpful. Okay, so that's in a nutshell, that's degrees of freedom. The slide set that we have for today is random effects. Okay, so about 2 or 3 years ago, we changed the curriculum for the 6611, 6612, and then longitudinal. We actually modified these courses and put more advanced material in 6611, and kind of sped it up a little bit. So what you guys have is actually more a sped up course compared to what it was like 3 or 4 more years ago. And the reason why, for many years it was taught like using more, some of the more even simpler methods, is because we have other students taking the course, students other than, biostats. But we finally decided, and I think it was appropriate, to speed the course up. And thus, we had to move a lot of 6612 into 6611, and then a lot of longitudinal got moved into 6612. And so you guys may have, that's why this really, I put it now in review. And I didn't even really teach this slide set until like a year or two ago. The class just decided we really like to see more on random effects. So you guys may have seen the slide set or a portion of it. Some are saying no. Did you talk about random effects at all in linear mixed models, like the theory side of it? Can't remember too much. I hear like kind of the.
We didn't really talk about the theory.
Okay, not really the theory, just the here's a random effect and here's how you fit it type of thing.
Mm-hmm.
Okay, so then
inference, and if you make it a random effect, can you or cannot interpret it, but not the theory.
Okay, so then this is a little bit of review and maybe some new stuff as well. And it's important, especially like if you really haven't talked about it at all. I think it's definitely worth spending some time on. So we're talking about inference for fixed effects in a linear mixed model. And then with some data, showing, so that part may be more review, getting a data set, but it's actually more complicated data, and we'll do up to quadratic random effects for that. And then at the very end, talk about tests for variance components. So there, all of the slide set material, for more detail, you can look at the course notes if you need to. So estimation and tests for random effects. We know, just to kind of step back for a second, we have a mixed model, and we have fixed effects, we have covariance parameters. Those are all parameters, right? And what we do is when we estimate them, we're using the marginal model. So the distribution of y, we form our likelihood. We can estimate the fixed effects, the beta coefficients, you can say, and the covariance parameters. We estimate those with maximum likelihood estimation, or REML. But we have random effects in the model as well. And so the question is, how do we perform inference for the random effects? A really natural approach is to use Bayes methods for this. So, and in particular, empirical Bayes methods. And it's natural for a mixed model, which I'll explain here in a second. But these estimators, I really like them because they're very intuitive. They end up being involving a weighted average of personal and group level data. And the way that you determine the weights depends on the data that you have. And again, we'll talk more about that. So a couple intuitive examples. Do you have any baseball fans in here? Nobody? Nobody's a baseball fan? No one watches the Rockies or the Dodgers, or, well, hopefully you know enough about baseball to understand my little example here. When the season starts, so there's a lot of statistics that are developed for baseball. And that's actually an area of science called sabermetrics. So some people go real crazy with the statistics on baseball, and I think it lends itself well because there's a lot of games, and I don't know, somehow just the following of baseball really is natural to all these statistics that are developed for batting averages, for pitching, for fielding, and so forth. So at the beginning of a season, batting average, and they write it as a decimal number like this. So instead of like a percentage, it's actually a decimal number. If you haven't had any hits, then you have 0.000. So to 3 decimal places is typically written. If you've hit every possible time, it's 1. Okay. And so like after a handful of games, you may have one of these percentages or decimals, right? So one of these proportions. Obviously, the more you play, at some point you're going to get a hit, and at some point you're going to get a miss. And so after a while, these batting averages tend to channel into a range of about 200, we say 200 to 350. That's a pretty standard range of percentages for batting averages. So if you consider like estimating what a true batting average is for somebody, early in the season, you don't have much data for a subject. So what you would probably do is you would take a weighted average that was based more on the team's average or even the league's average for that subject, and then less on what that subject's actual average was. Whereas as the season goes on, you have a better idea of how good that batter is. And you can use their average and maybe a little bit of the team average or the league average mixed in with that. And that's what an empirical Bayes estimator would do. Okay, so depending on how much information you have, you're gonna put the estimate more towards the subject or more towards population average. Okay, so that's kind of the idea. Another example would be estimating prevalence of disease of illness for individual counties, let's say in Colorado. Okay, so there are a number of counties. How do we get good estimates of prevalence of, maybe it's COVID or something like that? If there's not much data in the county, but there's a lot of data in the state, you could take whatever you have for that county, use that, and do a weighted average of that with the state level, which may be more accurate. Okay, but as that county gets more information, you may be able to use more that estimate more if you were to compute an empirical Bayes estimate of the prevalence in that county. Okay, so a couple examples there to give you the intuitive idea. So the Bayes formula, you guys I'm sure are familiar with this. This is in terms of the random effects and Y, where Y is, we're talking about our mixed model. So we have, we're in this framework, so just keep that in your mind. We're talking about the mixed model. And so when we, Y is our outcome. I call that data, okay, but we model it this way with the mixed model. So the question is, if we've talked about the two distributions that are important in the mixed model. And so the distribution of Y and then we have a distribution of Y given the random effects, right? That's what we have. But what we want to try, when we do inference, what we really want is a distribution of the random effects given the data or given our outcomes, right? Well, Bayes formula then becomes a natural tool for us to use because we can express the distribution of the random effects given the data as a function of what we have. Okay, so that's why Bayes formula and Bayes methods make a lot of sense for the random effects. And if we look at the mean of the posterior distribution, then we have a natural formula to estimate the random effects. So here, what we end up with, this is, let's see why. Need a good circle here. So what we end up with here is that's based on a mixed model that I wrote above. So we have a formula that tells us how to compute those random effect estimates using the Bayes method approach. So what is G? That's the covariance matrix for the random effects. Z is a design matrix, right? V inverse, that's the inverse of the variance of Y. And we have Y minus X beta. So that's our Bayes estimator. And the difference between a Bayes estimator and an empirical Bayes estimator is the empirical Bayes estimator, you just plug in estimates for those unknown parameters. That's the only difference. Okay, so the empirical Bayes estimator is computed by replacing unknown parameters alpha and beta with their maximum likelihood or REML estimates. Okay, so we have a good methodological approach to estimate the random effects, and we're going to do inference for that but before we get to those slides, again, to think about these estimates and the subject level data and the population level data, we can take the predicted value. You know, we talked about predicted values for a mixed model and how there's two types. There's one that's X beta hat plus Z B hat, and then the other one is the X beta hat. But if we're considering these type of random effects that add in the, we talk about these predicted values that add in the random effects, then we can express this based on the previous formula. We can express this as, we can think of this as the population average piece, and then this is the subject piece. And we're taking a weighted average where the weights are the RV inverse and then the I minus RV inverse. So in a nutshell, if your subject data is, if you have less subject data or it's more variable, you're going to weight the subject piece less, okay, relative to the population average piece. If you have more subject data or it's less variable relative to between subject data, then you're going to weight it more. Okay, so it's a natural way to weight subject level data with the population average. Again, thinking about those two examples that I presented, you know, you can maybe keep those in mind as well. So we can think of the predicted values being shrunk towards the population average, depending on how strong that subject data is. It's not shrunk back to the mean very much if the subject data, if you have a lot of subject level data and if it's less variable. Okay, that's the basic principle. So just to show you really quickly, you know, with the fitness data, we already talked about, and I showed you this graph. These are predicted values for the fitness data. And if you recall, subjects were in a fitness program and they got more fit as the weeks went on. And there were two programs. There was the low intensity and high intensity. One of the things I want to show you from this though is that if you take the general linear model predicted values, those are in red, the dashed red. And if you look at the empirical Bayes estimator, like the BLOOP, we call them the, you know, the best linearly unbiased predicted values. Those are essentially the I was going to write it, but this is a PDF, so I'll have a harder time with that. So these are the Y hat equals X beta hat plus ZB hat, and those are the blue lines. And you can see that if the overall average is here in the middle, those are pulled in towards that overall average more than compared to the red dashed line. So you can see that principle happening, that those predictive values are being pulled back towards the middle, but really not that much, just a little bit. Okay. Any questions so far?
So I guess, like, what would be the reasoning for using one type of predicted value over the other?
So we would if you're modeling longitudinal data, like we would use a mixed model or something like that, right? And if you do that, then you're going to end up with, like, if you use the regular approach, then you're going to end up with two choices, okay? So my comparison with what I showed you, you probably would not do the GLM approach, right? But that's just what I did, that just to illustrate the shrinkage effect. your choice, if you do a mixed model, your choice is going to be between the predicted values. So those are the x beta hat plus z b hat versus the predicted mean, which is the x beta hat. And so you would use the predicted values, the subject level ones, if you're interested in inference for individual subjects. Whereas if you're just interested in the averages, you know, like program effects, program by time, or time effects, or just those fixed effects, then you'd use the predicted mean value. So those would really be the two choices that you have. I think that the mixed models, the standard approach is to use the empirical Bayes method. So if you do consider those subject level predicted values, that's just usually what's used.
Okay.
Any other questions? So there's some slides here in the middle that I'm going to probably spend a little less time on. They're essentially talking about we're going to do inference for these random effects. So we get estimates, right? So I gave you the formula that will give you the estimates of the random effects, and then you can add that to the you know, other parts of the model to get predicted values, right? So you can get your x beta hat plus zb hat, and that will naturally, they may be shrunk back to the mean a little bit depending on the variability in the subject level data. So we understand that part. To do inference, so what else do you need? You typically need the variance of those estimators. Okay. One of the wrinkles, though, like here's the variance of the beta hats, or not beta hats, b hats. So these are the variance of the random effects, and we have the formula for that. But what we end up doing is actually using, because that's actually a random, we're doing inference on random effects and not fixed effects. And for that reason, we're going to get a better inference if we use, instead of using variance of b hat, we use variance of b hat minus b. So we're considering how far away the estimator is from the actual random effect value. And that's what's used in the t-test, because it's going to account for the variability in the random effects. Okay, so when you do the default t-test, if you add a random statement and you have the slash and then you write solution, you're going to get default t-tests. This is the variance that's going to be used in the denominator of those t-tests. So for example, like if we do just for a simple random intercept, our t-test can reduce down to our random intercept for a given subject divided by the standard error of that estimate minus the actual value. So that's what our t quantity would be for our test. And that would be testing for that one subject. Is their random effect estimate 0 or not? Okay.
Question.
Yeah.
In reality, is the random effect existing?
Yes.
Because like,
yeah.
like,
so go ahead. Finish. Go ahead and finish, Ben.
Like we have the outcome, we know it is there, but for this random effect, we have to estimate it first of all. So how do we do the two estimations at the same time and say one is the original and one is the estimate?
Yeah, so that, I mean, that's true. Is like we don't, the B, we don't see, you're right, we don't see that. But we can develop a formula for the test statistic that considers that value. So you take, you know, the estimate, which we actually do get, and then there's some hypothetical random effect value for a subject, we don't observe that. But what do we know? We have an assumption that those random effects are normally distributed with some mean. And well, the mean we assume is 0 and some variance, right? So you're right that we don't see those, and that's a good point. But we have this model that assumes that those random effects have some normal distribution with mean 0 and some variance.
Okay, thank you.
That's a good thing to point out. So yeah, another question.
I might just be missing something, but to do t-tests on random effects like this, are you really just doing this when you're trying to build the model and trying to see what random effects you should be putting in, like other slopes or something? Because usually you just treat them as nuisance parameters and then not do inference on them.
Yeah, you're right. So a lot of times we're not that concerned about the random effects themselves. You know, I can give you some examples, like with my COPD gene project, we have different sites that are conducting the research. And so subjects go in, patients go into these different sites. And for CT measures, there's different scanners that they use. And so we add in random effects for site because we want to account for the variability between the sites, but we're not really interested in those, right? And the same thing for scanner model. They could get different results based on the scanner model that they're using. So we have a random effect for the scanner model. And even the subject, we have a random intercept for subjects as well. And we may not be that interested in those different random effects, but we want to put them in the model. In that case, you don't need to do the t-test. Okay, so you don't necessarily need to do this, but in other cases, there may be data sets where, yes, you do want to do inference and you want to see for the subjects in your data for what other random effect you may be modeling. You are interested in understanding if particular subjects are significantly different than the mean. So it just depends on the research that you're doing. A lot of data sets you may not be concerned about. You just want to account for that nuisance variability. So in that case, I'd say you don't worry about doing the t-test, but there are some data sets where that may be of interest.
Can you use these t-tests kind of like traditional modeling where you decide if you're going to leave a random effect in, like a cluster analysis, and you're like, should I do a random effect for gender or something? Can you look at these t-tests and say, I don't?
You could, yeah, you could look at the t-test, but you could also just look at the variance itself, you know, because we do get an estimate of the variance. And if that variance is small, then that would also tell you that, you know, you may not need a random effect for that particular term.
You mean the outcome variance, right?
So like, no, for the, you know, like for the G matrix, you have a variance for like the random intercept, or for the example I described, you have a variance for the sites, or you have a variance for scanner model. And those you get, you know, when you look at your output, like if you look at the covariance parameter estimates, you can see the variance for those specific random effect terms. So that would be different than like the variance of Y that we've determined before. And you can also actually do tests of significance for variance parameters. And I think that's the last slide on this set here. But yeah, some good questions. So some of these slides I'm going to go through a little more quickly here in the middle. The one thing that I wanted to mention, and this is again just this sort of showing you a specific example. If we have a model that has just a fixed intercept and then a random intercept for subjects and error, just to demonstrate again the Bayes methods and how they're calculated. We can see that the random effect estimate in this case becomes the difference between the average of the subject's data and the fixed population average. But then we have this shrinkage factor, which is this lambda, and that is this quantity here. Okay, so again, you can see depending on the variance of the between subject relative to the variance of that includes that plus the within subject variability, that's going to be this lambda factor. And if you then add that in with the population intercept to get the predicted value, what the predicted value would be, you can see that we have this is the same thing that I'd shown before, but more a specific example where we have the subject level data. So what's your best guess? You know, if you only have that subject's data, what would you use? If you don't have time as a predictor in the model, well, you just average out their values, right? If you're measuring FEV1 and you take a bunch of FEV1s, what's your best guess at their true mean FEV1 would be the sample mean, right? But if you don't have a lot of good subject level data, then you can average that in with the population average. And the degree that you're averaging that is, you know, the weights that you use in that average, this lambda, incorporate the variability of the subject level data with the between subject data. And so this is the same principle, just showing you a specific example. And then what the variance of B hat would be, and the one that we really use in the test would be the variance of B hat minus B. Okay. So jumping a little bit, but the basic idea is we use Bayes methods to do inference for the random effects in a mixed model. And the inference, specifically the inference that we do is we use t-test methodology to do that. So you can perform tests, you can do, once you get your estimate, you compute confidence intervals using the t-test methodology. And of course, we also get a variance for the random effects, but that's using the marginal model, right? Because we estimate the fixed effects and the covariance parameters using the maximum likelihood method. So inference in general in a mixed model, you have two different pieces of it. The piece where you use the marginal model to estimate the fixed effects and the covariance parameters, and the piece where you use the conditional model to do inference for the random effects. This data set, I'm not sure if you guys, I'm guessing you probably did not see this before, but this is interesting data. This is data that a friend of mine who was actually on the cross-country team with me in college, I ran into him like 20 years later on the street, and we started talking and realized that he's working at CU, and he said, hey, I have an interesting data set involving climbers of Mount Kilimanjaro in Africa. It's this tallest mountain in Africa. And so he has data that tracks these climbers of Mount Kilimanjaro. And one of the things that he was interested in looking at was, does taking medication help people with that get high altitude sickness. So by taking medication, does that alleviate symptoms of high altitude sickness? The data that I'm going to present here looks at these climbers, and it looks at the altitude that they're at a given time. So we're tracking them as they climb the mountain. So these are longitudinal data, and we're measuring oxygen saturation. Normal range is greater than 95%. So you want this oxygen saturation value to be as close to 100% as possible. But the thing is, as you go to higher altitude, naturally, your oxygen saturation is going to go down. If you're really, really fit, it may stay high. But for most people, it tends to go down as you go up higher in altitude. So one of the things we looked at was for people that were pre-treated with a certain medication, did that allow their oxygen saturation values to stay higher? Okay. So here's the data, and here's a bubble plot. So the reason why we use a bubble plot here is because if you just do a scatter plot, you're going to get points on top of points, and you're not going to be able to tell very well how much data you actually have. So this is a graph that allows us to see that there were more subjects, like if you look at this band here at about 4.5 kilometers altitude, so about 4,500 kilometers. This is pretty high up in altitude. So we can see that you have a distribution that kind of looks like a normal distribution, profiled, where you have more values in the middle and then you have tails on the ends. And it's a little bit skewed because you have more values on the lower end down here compared to the upper tail. But either in SAS or R, I think R probably does bubble plots as well. But I did this one in SAS. So that's the data. These are the bubbles for the data. And then I fit a model that allowed a quadratic relationship between altitude and oxygen saturation. And there's two curves. One is for subjects that were pre-treated with this medication, and the other one where they weren't. So this is just showing you the fixed effect estimates. And the ones that were pre-treated, that's the blue line. And the ones that were not is the red line. Okay, so is there a significant difference there? Like visually, they don't seem that different, but there's a lot of data here. So we're able to significantly say that they're different. Now, is it worth it? Is it worth taking the medication to get that much of an improvement? That's the big question, right? Just because it's significant doesn't mean it's necessarily clinically important. But at any rate, our job is to show significance, right? So we can show that if we compare it at fixed altitude, we can show that the average values are significantly different. The way that I modeled this, this gives you the SAS code for it. So oxygen saturation is the outcome. X is altitude. So X is altitude. Diamox ever. That's a 0 or 1. So it's a 1 if they took that medication, and they typically started it before the climb for this particular one. There were other medications they took as needed, but this one they typically decided, I'm going to try this because I think I may, I'm the type of person that might develop symptoms, or I have in the past, so I'm going to decide to do this from the beginning. One thing that you notice though is that despite the fact it's really a class variable, I did not put it in the class statement. So this is basically this is a full rank approach. And I think if you just have a binary variable, And if you code it 0, 1, I often do that. You know, and I talked last time we had the big discussion about less than full rank models and all that. And I'm trying to argue, well, they're important at least to understand what we are able to do, right? But in practice, if it's just one variable and it's binary, a lot of times I won't put it in the class statement. I'll just make it an indicator variable. There's some ease of the process in doing that. So that's what I did here. But it does have implications when you write your estimate and contrast statements. Then it's essentially, we're treating it like it's a continuous variable. So you're just going to have one value, right? Instead of having two levels for it, having the no diamox ever and the yes diamox ever, we just have a 1 if it's present, right? And then and a 0 if not, but it's just one value since I did not put it in class statement. So again, that's another important thing to remember when you're doing approaches. You have a choice, which one are you going to do, and just the implications of it, important to remember. So we have our model. I have linear and quadratic terms for altitude, and then I have the diamox ever, and then I'm allowing interactions here so that we essentially can get a separate quadratic fit for the two groups. And I'm getting both predicted values because I want both. I want both the predicted mean values, and that allowed me to plot that line, that curve for both groups. And I also want the subject level predicted values. And that's what we get with the out P statement. So again, I mentioned this before, but this piece, that's going to give us our y hat equals x beta hat. And this one is going to give us our y hat x beta plus CV. Okay. And I did put solution in the model statement. That gives us the estimates of our fixed effects. And I put the solution in the random statement because I do want to see those t-tests. I want to see subjects, and if particular subjects were deviating from the population average significantly. So I have random intercept, and then I have altitude and altitude squared. I think based on what we talked about with degrees of freedom, I would probably, like, it doesn't matter in this case. The data set is so big, they're going to be pretty equivalent, but we could ask it to do a specific degrees of freedom method here. And you see the different tests that I've conducted here and estimates. So at an altitude of 1 kilometer, what's the difference between the two groups? At 2, 3, 4, 5, and then is there interaction between, if you compare over altitudes, are there differences between the diamox ever and not ever groups? And then a curve comparison. So there's a number of tests that I've asked it to do. And here's the abbreviated output. There's some interesting things that you see for this data set. Well, first of all, we have a really big data set. You can see that number of records used, almost 14,000. So it's a really big data set. So it shouldn't be too surprising that a lot of the effects are significant. But there's some curious things that we see with the G matrix and with the solution for random effects. And those are, G matrix is not positive definite. And you get a warning for that. And that's because this entry is essentially 0. Okay. Now the question is that a deal breaker? Is that something that we should say, this model didn't work? It didn't fit because we have a positive definite G matrix. And I would argue that it's not a deal breaker, because what we really are interested in ultimately is V, right? So we know V is equal to Z transpose plus R. So this is the thing that we're most interested in terms of getting a good model. And even if if we don't get we're not able to estimate that variance for the intercept, we could still get a meaningful V matrix, and that's the most important thing. So if you, I would say here, I'd say usually not a deal breaker. But I would say,
Question.
yeah.
Doesn't that mean that the maximum, so that your maximum may not be a global maximum, but it may be a local?
No, I think so. So what you're talking about, that's not related to what you're talking about, but that's a good point. If you see an issue like not a global convergence, if you get some information that suggests that you didn't converge to something that's based on the whole scale, or if you see something like the Hessian matrix is not positive definite.
Mm-hmm.
I would say those are deal breakers. So those are the things that you need to look out for. Okay, but the fact that you didn't estimate one of the variances in the G matrix, in terms of the model, the whole model fit, that's not a deal breaker. The one thing that it does cause problems with, I think, or it may be related to this issue as well. We were not able to estimate standard errors for the intercept and for the linear term. So you ignore these things here. Okay, these are not. It's not that these are really significant, but we didn't. The model fit did not allow us to do this. So I would not do any of the inference on these specific terms. It looks like for the quadratic term that those make sense. So I think we can do that, but that's one of the downsides. Like what I would try to do with this model would maybe try to refine the model. If we really wanted to inference for all three of these pieces, if that was important, then I think we would try to tweak the model. But in terms of estimating the fixed effects and doing inference for the fixed effects, and then doing inference for the quadratic effects, we're able to do that in this model. Okay.
So that, I just want to make sure I understand what the t-test is telling you. For each subject, it's telling you whether that curve is actually quadratic or not.
That's a good question. And what it's telling you, remember that you can think of the random effects as deviations from the population average. So this first one, negative 0.82, that's the deviation from the population average quadratic piece. So it's saying, is the quadratic stronger or weaker than the quadratic for the population? That's what it's testing. And so for this first subject, you would say their quadratic is at the 0.05 level is significantly less than the population average. And I actually have I show a few examples. I'll get to that in a second. So the test, we have the estimates and the contrast based on the tests that I wrote before. And Carrie, for the question that you just asked, so here I plotted all of the predicted values. These are the subject level predicted values. But specifically, let's look at one of the predicted values for a subject in the no diamox group, and then another for a subject in the yes diamox group. Now, you look at this curve. Does that look more curved compared to the population average, this red line, or the red curve?
Yeah.
Yeah, it does. It does look. What about this blue one? Not as much, right? At least compared to the red one. This red curve, this subject's curve, seems more pronounced compared to the thick red line than the subject here in blue compared to the population counterpart. And so the tests, if you go back and look at the tests, where did I put that? Oh, here it is. Okay, so this would be the one. This would be for the red one, and this would be for the blue one. So it sort of matches visually with what the tests tell us, that the quadratic curve is significant for that one subject compared to the population average, while it's not for the blue one.
And its value would be, its actual estimate would be positive because it's a stronger curve. Like the blue one would have a negative effect and the red one would have a positive effect.
I think if I'm looking, if it's the subject, I think it's more negative because it's concave down. I think that's the way it's working here. So if it's concave up and it's more curved, then it would be more positive.
Right.
But since they're concave down,
More
and
negative.
it's more curved, then it's more negative. I think that's how it's working. The last slide is just a comment on the test for variance components. You can do that by adding the Cove test option in ProcMix, and I'm sure there's an equivalent in R to do that. I don't often do this. I'm more concerned about the relative variances to each other, and you get an idea if they're important or not, I think, by just looking at the relative magnitude of the variances. But you can do actual tests for significance for them. So this would be for the variance components, and those are fixed parameters in our model. Okay. Any questions on the presentations here for anything that we've talked about today? So give me like 10 to 15 minutes and I will be back for office hours. So I'm gonna stop, let's see, recording.